A function is a set of ordered pairs where each x value corresponds to only one y value. Looking at the relation f, notice that 1 only corresponds to 3, 4 only corresponds to -7, and so on, -2 to 0, 5 to 0. Each x corresponds to exactly one y value, making this relation a function. To find the inverse of a function f, we switch the x and y values in each of the ordered pairs. In this example, f inverse we can write as 3, 1. Notice we just switch the x and the y coordinates of the first point. And then we would have -7, 4, 0, -2, and 0, 5. This is f inverse. Notice that f inverse is not a function, and that's because the x value 0 corresponds to -2 and 0 corresponds to 5. That particular x value corresponds to more than one y value, which means f inverse itself is not a function. To find the domain and range of f, we look at the x and the y values. The domain of f will indicate that domain with a subscript of f is 1, 4, -2, and 5. It's the x values of f. The range of f will be the list of the y values, 3, -7, and 0. We only need to list it once. And then the domain of f inverse. The domain of f inverse are the x values of f inverse, 3, -7, and 0. The range of f inverse are the y values of f inverse, 1, 4, -2, and 5. Notice that the domain of f is the same as the range of f inverse, and the range of f is the same as the domain of f inverse. A function f is one-to-one if its inverse is also a function. In this example, let's determine whether the functions are one-to-one. Notice that Dan maps to Saturn, John maps to Pontiac, Joe to Honda, and Andy to Pontiac. Each driver maps to a single car, so we know that it's a function. But is the inverse also a function? Notice that Saturn maps to the driver Dan, Pontiac maps to John, and Pontiac also maps to Andy. Honda maps to Joe. If we look at it in this direction, we can see that Pontiac maps to two separate drivers. So the inverse is not a function. Since the inverse is not a function, we can say that this mapping is not one-to-one. In the next example, we can see that 1 corresponds to 5, 2 corresponds to 8, 3 corresponds to 11, and 4 corresponds to 14. Every x corresponds to exactly one y value. So we know that s represents a function. Is the inverse also a function? So read it backwards. 5 corresponds to 1, 8 corresponds to 2, 11 to 3, and 14 to 4. Every y value corresponds to exactly one x value, which means the inverse is also a function. And since the inverse is a function, we can say that s is one-to-one. Let's sketch the graph of f inverse and determine whether or not f is a one-to-one function. Using the graph of f, we can get some points that are fairly obvious. it looks like negative 2, 0 is a point on the graph of f, as is 0, negative 4, and 2, 0. Recall, to find f inverse, we simply interchange the x and the y values. So negative 2, 0 would become 0, negative 2. Zero, negative 4 will become negative 4, 0. And 2, 0 will become 0, 2. We can use these points to sketch f inverse. Now we can use the vertical line test. Recall that the vertical line test says that if a vertical line passes through more than one point on the graph, then the graph does not represent a function. Looking at f, if we draw a vertical line anywhere on the graph, we can see that it will only intersect the graph one time, meaning that f is a function. However, if we draw a vertical line on f inverse, notice that it intersects the graph more than once, which means the inverse does not represent a function. And since the inverse does not represent a function, we can say that f is not one-to-one. We can use the horizontal line test on the graph of f of x to determine whether or not it is one-to-one. If a horizontal line passes through more than one point on a graph, the graph does not define a one-to-one function. For example, let's graph the function and use the graph to find the graph of its inverse function. G of x equals x squared plus 2. Without the extra condition of x being greater than or equal to 0, we can think of that as the basic quadratic that we're familiar with. This particular graph fails the horizontal line test, meaning it doesn't have an inverse. But if we take into consideration the extra condition of x being greater than or equal to 0, we can remove this portion and just look at the portion where we have the domain restriction. X is greater than or equal to 0 now, and it passes the horizontal line test, which means it has an inverse. So we can use these points 0, 2, and 1, 3 to get G inverse. To do that, we simply switch the x and the y values. So 0, 2 will become 2, 0, and 1, 3 will become 3, 1. And we draw that curve. Looking at the graphs, we can find the domain of G. The domain of G, remember, are the x values. So we have 0 to infinity. The range of G are the y values, 2 to infinity. And then the domain of G inverse, again, x values, 2 to infinity. And then the range of G inverse, 0 to infinity. Notice that the domain of G and the range of G inverse are the same. And then the range of G and the domain of G inverse are also the same. We can algebraically test for inverses. If f composed with its inverse equals x, or if f inverse composed with f equals x, we know that they are truly inverses of each other. For example, let's determine whether the functions are inverses of each other or not. We'll start by composing f with g. That is 3 times x. We're going to replace x with g, x minus 2 over 3. Then finishing off f, we have plus 2. If we distribute the 3, we get x minus 2 plus 2, and that is equal to x, which is what we wanted. We can also do it the other way. We can compose g with f of x. So we'll write out g, but instead of writing x, we're going to replace that x in the g function with f of x. That is 3x plus 2. And then simplifying this, we get 3x over 3, which is, and since we compose f with g and the result is x, we can say that g is f inverse. They are indeed inverses of each other. We'll use this process to check our answers when finding an inverse. The steps to find the inverse of a one-to-one function are 1. Replace f of x with y in the equation. Step 2. Interchange all x and y values. In other words, you replace all the x's with y and all of the y's with x. Step 3. Solve the resulting equation for y. 4. Replace y with f inverse of x. And step 5, we can check to see if we have truly found the inverse. Step 1. To find the inverse, we first replace f of x with y. Next, we switch the x's and y's. So the y we will replace with x, and the x we replace with y. Next, we isolate the y, get y by itself. Start by subtracting 7. We'll do that on both sides. And then we divide by -2. Once we've isolated the y, we can now call that f inverse of x. So we have the inverse. To check this, we can find f of f inverse. So we're copying the f function, but every time you see an x, you're going to replace that x value with what we think f inverse is. Now simplify. The -2's will cancel, and we are left with x, which is what we wanted. If we do f of f inverse or f inverse of f, and the result is x, then we know that we have truly found the inverse. In the next example, we're again looking for the inverse. We'll start by replacing f with y. Up next, we switch the variables. The y becomes x, and the x becomes y. From here, we need to isolate the y, get y by itself. We can multiply by the LCD on both sides. This will give us 2x minus xy equals 4. Continuing to isolate the y, we next need to subtract 2x on both sides. And finally, we will divide by -x. Once we have y by itself, we have found f inverse. 4 minus 2x over -x. To check to see if this is truly the inverse, we can evaluate f of f inverse, and hopefully the result will be x. So we're going to copy f, the original function, 4 over 2 minus x, but instead of writing the x, we're going to replace the x with f inverse. 4 minus 2x over -x. Checking this example is a little bit more tedious since we have a complex fraction, So we first want to simplify the complex fraction. We can do that by multiplying the numerator and denominator by the negative x, the smallest denominator. In the numerator, we get negative 4x, and in the denominator, 2 times negative x is negative 2x, and then negative x times the fraction, the negative x's will cancel, and you're left with just the numerator. We just need to make sure we distribute the negative sign, so negative 4 plus 2x. Continuing to simplify, in the denominator, the negative 2x plus 2x will add to 0. We have negative 4x over negative 4, which reduces to x. And since f of f inverse gave us x, we know that we truly found the inverse. To find the inverse of this function, we start by replacing f with y. Up next, we switch the variables. X's become y's and y's become x's. And now the goal is to isolate the y. We can start that process by multiplying by the LCD. On the left, we distribute to get 5x plus 4xy. On the right, the denominator will cancel with the LCD, leaving us with the numerator 3y minus 3. Keep in mind, the goal is to isolate the y, so we need to move terms that contain y to the left side. Terms that contain x, we will move to the right side. We now have 4xy minus 3y equals negative 3 minus 5x. On the left, we have two terms that contain a y, so we need to factor out that y, leaving us with 4x minus 3 equals negative 3 minus 5x. Finally, we divide both sides by the parentheses, and we get y is equal to negative 3 minus 5x over 4x minus 3, which we can now call f inverse of x. To check this, we evaluate f of f inverse, and hopefully the result will be x. If we get x after evaluating, we know that the inverse is correct. So we're going to write out f, but we're going to replace the x's that are in the f function with f inverse. F inverse was negative 3 minus 5x over 4x minus 3. Since we have a complex fraction, we want to simplify that by multiplying by the smallest denominator, 4x minus 3, over itself. This process gets a little tedious. 4x minus 3 times this first fraction will cancel the denominator. You're left with just the numerator. So we have 3, and we need to distribute that with the numerator. We get negative 9 minus 15x. And then we need to distribute the 4x minus 3 with the negative 3. That will be negative 12x plus 9. In the denominator, the 4x minus 3 will get distributed with the 5, giving us 20x minus 15. And then the 4x minus 3 times this fraction will cancel the denominator, leaving us to just distribute the 4 to the numerator. That is negative 12 minus 20x. Continuing to simplify, notice the numerator, the 9's cancel, they add to 0, and then we get negative 27x divided by, in the denominator, the 20x's add to 0, and we're left with negative 27. Reducing that, we get x. And since f of f inverse resulted in x, we can say that the inverse we found is truly the inverse. Verifying the inverse can sometimes be more tedious than actually finding the inverse.